Okay, so what we've done up to this point, we went through the human power problem. We showed that humans are running at 121 watts. That's the equivalent of 10 megajoules per day. We then went through a little Microsoft Excel exercise. We know that humanity is running technologically at 500 exajoules per year. Oh, and this is engineering. We looked a little bit at scientific notation, engineering notation, and then put this in a per capita basis and came up with this term technoslaves, of which the average human on the planet has 20, average North American has 120 in terms of our consumption habits. All right, so let's go into the course now, and I want to just start looking through chapter 1 and make sure that we're on schedule for our exams. I had a first semester student come in today. He thought he was like behind in everything and failing and hadn't turned. I'm like, no man, it's week 1. Like nothing's due week 1, especially like after like, it's okay. And I guess I'd rather have you a little bit panicked on Thursday rather than panicked at midterms and you haven't cracked the book or anything. But it was sweet. If you don't have the textbook yet, I've got, it looks like most people have the textbook. It's sitting right here. We had them scanned. This is the 3rd edition of this text, and let me just look at the publication date. 2012, so it's 3 years old. They updated it. Well, it was 96, 04, 2012. So the next edition, if in fact there's going to be one, is not till 2020. And I can guarantee that the information in the book changes more quickly. I mean, there's your relativistic time. The rate of change is only going to sharpen. It's only going to become greater. Let's just take a look here, and I'm just gonna open up the figures. I find that the most effective way to flip through the book, hit the highlights. Tim Chester, who introduced himself on Tuesday, is going to be mainly responsible for grading the summaries and the exams, so I think you know what to expect there. I'm going to do my best to bring some guest lecturers in, but I'll be primarily.
Are the tests online?
All the tests are online. If you need to print the thing out, though, we can print it. We can print if you're more comfortable, just take it on a pencil paper. That's not a problem. Okay, so we dug a little bit into the relationship between energy and power. This little figure shows about what a single joule of energy is. We talked about what its heat equivalent is. The heat equivalent of a joule is raising 1 cubic centimeter 1 degree Celsius. So I'm trying to think. If you had a fine capillary tube and heated that little bit of water, it would expand, and you could actually raise an apple with it. Right? It would have to be very well engineered, or you could use your hand. But what's being shown here is that to raise this apple 1 meter takes about a joule of energy. And since my other pad isn't working, let's just take a look at that. So we know that energy and work have the same dimensions and the same units. So both energy and work are measured in joules or calories or whatever. But conventionally, it's joules. So what's happening here is the person, the system, and if you remember from 101, in fact, it's the title of this course, it's renewable, it's not the title of the book, but it's the title of the course, Renewable Energy Systems. And so what we're looking at here is a system. The apple in the hand is one little system. The work is coming in through the human, and the work is being, so the human is spending energy and doing work on the apple. Well, how much? Let's look at it this way. So we know that energy, I'll just put as gravitational, equals mgh. So I like to just use the same symbol for units each time, so I'm just going to use E for energy. What's mass? It's the mass of the apple. M is the mass of the apple. What's G? That's gravity. And then what's H? That's the distance. So let's look at the units here for a second. The mass of that apple is, well, he's saying 100 grams. So M equals 100 grams. This is confusing because I just used a G for grams and it's also there for gravity. Better way to do that, and this is something I'd like to see in your summaries too, is to always italicize your variables. Oops. So I just did that. So I've got E for energy is italicized, the MGH are also italicized, this M is italicized. Now, if we run it like this, how many kilograms is that? 0.1, okay, 0.1 kilograms, perfect. What's G? What's the value of G? Gravity.
9.8.
Yeah, 9.8. So I'm just going to call it 10 meters per second squared. And then H, we're looking at 1 meter. And again, I'm going to italicize each one of those variables. So from there, I can just say that E equals, and I'm going to lump the values together. So 0.1 times, there's another way to put in a fancy times if you do it like that, times 10 times 1, and then let's put the units in, kilograms, meters squared, seconds to the minus 2. Okay, so hopefully you follow that. There's a couple different ways to put that seconds squared. One is just to put it in the denominator, so under the division. Another way to write it is just to say seconds to the minus 2. Same difference. Now, all I have to do is just, so pretty easy, 0.1 times 10 times 1 is 1. Now, the tricky part is looking at that thing, okay, what the heck is a kilogram meter squared per second squared? I think it's in the book. Let's just take a look. And this is just one of those things that I just kind of gotta know. Let's see, energy. I'm looking on page 532 again and seeing, I see joules. I don't see the breakdown of the units. There's nice conversions there. Let's bop out to a web page and see what we can do with that. Dimensions of energy. Whoa, that was fast. That was good. Okay, perfect. Keep an eye on this page. super duper important, fundamental to this course. Just a second ago, we looked at the dimensions of gravity, and gravity and acceleration are the same thing, and its length per time squared. We wrote it out as meters per second squared, and you can see right here, it's just length per time squared. Force is, well, it's mass times acceleration. So all you do is throw a mass on there. You multiply by mass. Now, to get to energy, you add an extra length dimension, because I'll write it like this: work equals force multiplied by distance. And what we're looking at right there, force is mass length per time squared, right? Mass length per time squared. Distance, well, it's just length. So work, I just said, 10 minutes or so ago, work and energy have the same dimensions. It's just mass length squared over time squared, or mass length squared times minus 2. All the same. Each one of those expressions is equivalent, thus the equal sign. And then finally, the last one down here is power is mass times length squared divided by time cubed, and that's just right back where we were at the very beginning of lecture when we knew that power was energy divided by time. So that there you pick up that extra time in the denominator. Pretty simple, pretty straightforward, and right there, that's kind of our bread and butter moving through the remainder of the text. So from that, we know that equals 1 joule. So I think somewhere in here we're going to have a definition. It's pretty fun to watch Google evolve. I mean, it was not quite this spiffy even last year. I somehow, well, I know the thing. You know the thing is learning, because what it's doing is, I'll type that little question in, and it'll go and see which one of the answers I pick up, and then it'll sort of combine, resolve, and to some extent predict what the next user is going to hit. So it's, yeah. And Wikipedia too. Yeah. Well, and so there it is. That's exactly what we did. The definition of 1 joule is a kilogram times meter squared per second squared, or newtons times meters. There are other ways to do it. We've already reviewed the fact that it's a watt second. Pretty cool also that it's a Coulomb volt. That's your electrical equivalent for energy. Okay, so that's just kind of giving you a flavor or a sense of what 1 joule is. We looked at it thermally in terms of raising temperature of water. Here it is mechanically. All right, we checked this out a second ago as well. It's the same exact figure that's in your 101 text. Now, what we're looking at here, just kind of digging down into the renewables. So this little circle is, well, it just took that little renewable slice of the pie and broke it out. That seems a little bit high to me. Let's check the math on that, because it's telling us 65 exajoules, but the number I saw a second ago was 4.7. Let's just run that and see where the discrepancy is. Anyone else picking up on that? So it's,
Total consumption for the world?
yeah, uh-huh.
Yeah, because then we have the value of 500 exajoules per year.
Right, right. Oh, I see where it is, because there's, oh, you know what, I got it. It's not that one little slice. It's taking other sources, traditional biomass, and hydro as your renewables. So let's take those, let's just double check here. So we've got, equals 500 times, and let's just write these out together. So .0 or 047, that's 4.7%, right? Check me if I'm wrong, plus 0.06, that's the 6% on the traditional, plus 0.023, that's the 2.3% on the hydro. So I've taken that 500 exajoules and multiplied it by those three percentages. Okay, there's the 65. I feel better. So when you're looking at these things, it's good to obsess a little bit over the numbers and double check it, and right there's a chance to kind of bone up on our Excel skills. So what we're looking at in this next figure are these three little pie slices in a single pie. And we can see that traditional biomass is the vast majority. It's weird to see how quickly solar is growing. I mean, there's a new PV setup goes up about every minute in this country, but it's still 1%. It's like 1 or 2%. So it's only going to grow. Geothermals. I don't know why he keeps calling me. Geothermal is small but growing. I think it's only going to take off, especially here in the Pacific Northwest. Hydro is fairly substantial. There's a big pumped hydro storage facility going in. I don't know if you heard of the Gordon Butte facility or not, but 800 megawatts. I don't know if we put that in hydro or not, but it's kind of good. It's more storage. It's not primary. And everything that you're looking at here is something you're going to call a primary energy source. So if you remember from 101, primary is something that's coming directly from nature. I guess in the case of the pump storage, that's a little bit more like your batteries. And you'll see right now, gosh, batteries are not listed among our primary energy sources just because they're storage. Yeah, question.
So, we're talking hydro, we're talking dams.
Hydro dams, exactly, yeah.
Okay, there's huge issues with that.
Yep.
They have caused horrible destruction and remapped everything.
Yeah.
I mean.
It's not getting better either. China's about to dam up half of Ecuador. It's bizarre, but yeah,
I recently watched a documentary on dams and how they got and why they were and the destruction
Yeah.
that they have caused.
Yeah.
I mean, and the issues of people wanting to take them down.
Mm-hmm.
And
Sure, it's true, and I think what we're,
something so destructive.
Yeah. Well,
being listed, because it's a matter of what kind of thing.
well, it's not, I mean, these aren't judgment calls, these are just like what the renewables are, and, hydro that come, essentially from sunlight that was pushing water molecules up in the air, they fall on the ground, get backed up by the dam, it's renewable, so they're not, making a judgment call, and I think what we're gonna find, honestly, Shelley, with this, it's a lot of times it's kind of pick your poison. I mean, people have issues with solar power too. I mean, a lot of the materials that go into them are toxic if they're not processed or disposed of properly. Same thing. I've got a buddy right now who is installing some wave tech off the coast of Washington, and I'm sure some poor whale or fish is going to bump into the thing, or they're going to figure out there's a EMF coming off of it that screws with some dolphin's navigation system. So there's no perfect solution, and a lot of times too, with the whole biomass thing, we've written some biomass utilization grants recently, and there's gonna be somebody that complains, like, I don't want you out, I don't want the lumberjacks out there messing around with Woodsy the Owl's house either, so there's no perfect technology, sorry. But, it is really important, though, that as a civilization, we realize what the downstream effects are and do our best to minimize them. So, no, I hear you. 300%. Okay. This is fairly up to date. Projection of conventional oil production. So this is just looking just at oil. And these are currently producing fields. If this number weren't going down, we wouldn't see Shell building its Arctic drilling rigs. I mean, why would you do that if you could still keep going after the conventional producing fields? So they will continue to be on the decline. These are the ones that might yet be developed. The entire world has not yet been explored. Russia put its flag in the North Pole. Like I said, Shell's going for Arctic oil. These are the ones that haven't even been found yet. So again, this could be a way to sustain production. Natural gas liquids, there are a number of ways. In fact, there are companies right now taking natural gas and converting it into octane. If you remember your chemistry, we'll just dip into that for a second. We know that methane equals CH4. So there's one carbon atom surrounded by 4 hydrogen atoms. We know that octane equals C8H. Remember how many hydrogen atoms are on an octane molecule?
Maybe like 16?
16 is a great guess. It's 16 plus 2, so it's going to be 18. Yeah, there you go. Yeah. And, whoops. When I forget, I always like the pictures better. So let's just pop out here. Octane. Oops. Octane. Thank you. And if we look at images, so there it is. There's your backbone. 1, 2, 3, 4, 5, 6, 7, 8. And then if you look at it in the linear form, and I think that's why you guessed 16 off the top of your head because you're thinking of those side bonds. Those 2 N guys are complete the bonds because carbon has those 4 orbitals that are available. But you can see how pretty straightforwardly, if you were to heat, compress methane enough, hydrogen is going to come off. Hydrogen will basically be a waste product or a byproduct, which is also a marketable thing. And then there's your nice steady liquid octane to burn. So that's where this figure is going. Natural gas liquid. So there's a lot of natural gas development going on, and so from there are refining processes to turn that right into octane and then put it into the transportation sector. Unconventional oil, this is your tar sands, worse energy return on energy invested, but it can't go on, it won't go on forever. We already talked about the fact that it's finite. All right, so that's global. If we now just drop into the UK, and this is kind of fun because it allows us to look at petajoules for a second instead of exajoules. So looking at this really quickly, what fraction of the world's primary energy does the UK use? do that little math, and let's figure out what fraction of the UK, or what fraction of the world's total energy it uses. I'll run that too. Oops, covered it up. I'm gonna call that 9,000 petajoules. Yeah, well, not, yeah, just run it up to 9,000. It's a little small. I'm only getting 2%. Is that what you guys got? Yeah. So 9,000 petajoules is the same as 9 exajoules. So right here, I just divided 9 by 500, and it's only 2%. It seems, yeah, it seems low. But I do know that the Brits, they don't drive nearly as much as we do, and I know a lot of their appliances are more efficient. But here's the breakdown. So delivered, so here's solid, very little coal delivered. Fair amount of liquid, fair amount of gas. This is electricity at the source. This is how much is lost. So of this total primary consumed, this is just kind of getting it there, right? And you could even think of it the same way as these coal trains move through Missoula. If they were run on coal, you could imagine at the end of the line, some fraction of those coal cars would be missing, right? Because they would be burned in the process of moving. So that's basically what's being lost. 4 major sectors. Again, this is standard. Here's what people use at home. Here's what's used in office places. Here's what's used moving the energy around. And this is industry, manufacturing, and whatnot. Now, if you break it out in terms of the use, this is space and water heating. This is industrial heating. So in general, things have to get hot. So you can think running forges, running manufacturing processes, things like that. Cooking, you might think it would be larger than that, but it's not. It's relatively minimal. I always watch these cooking shows and see how much energy goes. I'm like, oh my God, it's so wasteful. But it's still a tiny fraction compared to what else is going on. So transport's the same, lighting and appliances, and then here's machinery. And so this machinery could be in all of these different sectors. So for example, I would call a paper shredder a machine, and that's sitting there in your services sector. Okay, I think I might be running over, well, I'm right at 30 minutes. So I'm just going to stop it here so we don't go too long.